Okay, so our topic for today is magnetic forces. We'll start with force on a wire, and if you put a current carrying wire in a magnetic field, it will experience a force. Now, this magnetic field is not the wire's own field. We're going to call it the external field. That means it's coming from some magnets that aren't shown in the diagram. Now, it turns out that the amount of force that you get depends on several things. First of all, it depends on the length of the wire that's in the field, L. It depends on the current that's going through the wire, I. And then it depends on the external field strength, how strong that field is. But there's a little bit more to it than that, because it turns out that you only get force if the current's perpendicular to the field. If the current happens to be parallel or anti-parallel, then there's no magnetic force. So for instance, in this case, they're perpendicular, yes, there's force. Here, with the magnetic field going into the page, once again, there's force. But here, they're anti-parallel. There's no magnetic force in that case. Now, you can express that using a sine function. You can say something like LIB sine of theta. And then when they're perpendicular to each other, the sine of 90 is 1, and you get LIB. When they're parallel, you get either 0 or 180, and the sine is 0. But I tend not to do it that way. I tend to say that the force is just LIB external, and then just remember that things have to be perpendicular in order to get force. The current's got to be perpendicular to the field, or at least have some perpendicular component of magnetic field. So that's the magnetic force. Now, this force, remember, is a vector, so we need to think about direction. Well, it turns out that the direction is given by a right-hand rule. And here's what you do. You take your right hand and you point your index finger in the direction of the current. Then you point your palm or your middle finger in the direction of the magnetic field, and don't worry about the other two fingers. When you do that, the thumb of your right hand indicates the direction of the magnetic force. Now, what we're really doing here is we're doing a cross product. We're pointing a vector cross product. We're pointing our finger in the direction of, not really current, because that doesn't have direction, but you can define like a length direction for the wire, and we're crossing it with the magnetic field. And a cross product just gives us this behavior, that it's so it's perpendicular to both the current direction and the magnetic field in a right-hand sense. So let's do an example here. Let's find the magnetic force on this wire here. So we've got a cell and we've got a resistor here, so we can find the current just using Ohm's law. It'll just be V over R. So you can see we have 30 amps of current. It'll be flowing down in this direction here. There's going to be an external magnetic field coming from these two magnets. This may be like a horseshoe magnet. Magnetic field goes from north to south, so that's the direction of the B field. And the force will just be, because I and B are perpendicular to each other, it'll just be LIB. Now, L is the length of the wire that's in the field. That's this 22 centimeter length right here. I is the current, and we've already said that's 30 amperes of current. And then B is the magnetic field strength, which is 5.4 milliteslas. So multiplying those together gives us 0.0356 newtons of force. Now, in terms of the direction, you do the cross product, and the cross product in this case is going to give us a force direction. Well, first point your finger in the direction of the current, so your finger will point down the page. Then, keeping it pointing down the page, rotate so that your index finger or your palm points to the right. And when you do that, your thumb should be pointing directly out at you, so that this force direction is out of the page towards you. So let's show you that here. You take your finger of your right hand, point it down the direction of the current. Now you have to rotate your right hand so that your middle finger points in the direction of the magnetic field. And when you do that, the question is, which way does your thumb point? and your thumb is pointing out of the page. So this finger for current, this finger for magnetic field, thumb points out of the page. Okay, another example next. Let's find the force between these two wires. Now, by Newton's third law, it'll be an action-reaction pair. And let's say we want to find the force on wire 2. So we know that that force will be the length of wire 2 times the current that it carries times the external field. Now, the external field is being produced by, in this case, wire 1. So we have to calculate the field of the first wire. Well, what's the field of a wire? Well, the field of a wire, oops, not equal, sorry. Field of a wire depends on, or can be calculated, using the result we got from Ampere's law last time, magnetism constant, times the current in wire 1, over 2 pi times the distance we are away from wire 1, and the distance of interest will be this 5 centimeter distance there. So the length 2 is 50 centimeters, and all of wire 2 is in the field of wire 1. I2 is 6 amps. This will be I1, the current in wire 1, and we know the distance, and we know the magnetism constant. So if you substitute that in, you should find, first of all, if you work out this field separately, it works out to be 8 microteslas. So 5 centimeters away from a 2 amp current, the field is 8 microteslas. If you then multiply by the 50 centimeter length and the 6 amp current, you get 24 micronewtons of force on this second wire. Now, in terms of direction then, we grab wire 1 with the fingers of our right hand to find the direction of the field. And with your thumb pointing to the right, your finger should curl and go into the page down here. So this will be the direction of the field of wire 1. So that's using the magnetic field right-hand rule. For the magnetic force right-hand rule, you point your finger in the direction of I2, which is to the right, your middle finger in the direction of B1 into the page, and you should see your force thumb pointing directly upwards. So parallel currents actually attract. Let's try showing you that here using the camera. Wire and going into the page below the wire. So everywhere here, B1 is into the page. With the force right-hand rule now, there's the direction of the current. The field from wire 1 is into the page, so the force on wire 2 is directed up the page. All right, so that magnetic force is given by another right-hand rule. Once again, you point your finger, this time in the direction of the velocity. You let your middle finger point in the direction of the magnetic field. Don't worry about the other two fingers. Then your thumb is going to point in the direction of the force. This is on your right hand. The thumb will point in the direction of the force if the charge happens to be positive. A complication with this Lorentz force is that the charge could be negative, in which case the force on a negative is just opposite to your thumb. So let's try some examples here. We'll try and calculate the force on each of these particles. Okay, so now for the right-hand rule. You see the velocity to the right, the magnetic field is down. My thumb points into the page. So if it's a positive particle, which it is, the force would be into the page. The next example, the velocity is to the right, the magnetic field is down, my thumb points into the page, but it's a negative particle. That means that the force here, so this force was into the page, this force is coming out of the page. Third example, velocity is again to the right. This magnetic field is out of the page, so I've got to turn until my middle finger points out of the page. Now my force thumb points down the page. It's a positive particle. The force is in the same direction as my thumb. This example, the velocity is up the page. The magnetic field is in, so I have to turn like this, and now my thumb points to the left, but it's a negative particle, so the force is opposite to that. The force is to the right. Two more. In this one, the velocity is to the left, the magnetic field is into the page. My thumb points down the page. This force is down. The velocity is coming out at me. The magnetic field is directed to the left. So again, there's the correct right-hand rule. Again, my thumb points down the page. It's a positive particle, so the force is again down. So don't give yourself tendinitis doing this. Okay, so having practiced the right-hand rule a little bit, we're now ready for a numerical problem. So here we've got an electron gun, so we're going to shoot electrons. We're going to get them going really quickly. They're going to enter this region of magnetic field. The magnetic field is into the page. So if we do the right-hand rule, right index finger points to the right middle finger into the page. You should see your thumb pointing up the page. Because these are electrons, negative particles, the force will be opposite to that, so the force will be initially down the page. Now, for the speed, we'll use the electron gun relation that says potential energy gets converted to kinetic energy. If we solve that for speed, we'd cross multiply the 2, we divide by the mass, and we take the square root. So Q is the absolute value of Q. It's the charge on the electron, 1.6 times 10 to the minus 19. We're accelerating this electron by 220 volts. The mass of the electron you can look up, 9.11 times 10 to the power negative 31 kilograms. Then you take the square root, and you get the speed of the electron beam. Works out to 8.38 million meters per second. Next, the magnetic force. The force on the particle is QVB. Notice that the V and the B are perpendicular, so there's no component required. So we put in the sign of the charge, 1.6 times 10 to the negative 19 coulombs. The speed, 8.38 million meters per second. And then the magnetic field is given as 22.4 micro teslas. So that gives a force of 3 times 10 to the power negative 17 newtons. It says, I think 3.0. It could be 3.5 though. My writing's a bit messy. Solving for the acceleration though, you divide the force by the mass of the electron. I was a little bit more tidy here. I get 3.29 times 10 to the power 13 meters per second squared. So a really big acceleration. Now let's think about the subsequent motion of the electron. Let's assume that we have a really big region of magnetic field here. And let's draw some nice vectors here just to help us visualize this. So here's the velocity vector right there. And it's traveling to the right at a high rate of speed. Okay, now for the force vector, we just said by the right-hand rule that it was going to be directed straight down the page. Okay, now that means that a little bit later, if we look at this electron a little bit later, it's not going to be over here on the right anymore. Instead, it's not going to be over here because the force is going to have deflected it. It'll have deflected it down a little bit here like that. And the velocity is not going to be in this direction anymore because of the force. It's going to have required a downwards component. So maybe a little bit later it's now going like this. Well, the force vector is still going to be perpendicular to the velocity. And this is interesting because the force always remains perpendicular to the velocity. The magnitude of the velocity doesn't actually change. It's just the same. It's just the direction that's changing. So the same speed, but different direction. We'll think about that a little, or that will come back to us a little later. So next, we can just repeat that argument. A little bit later, the particle's not going to be over here because the force is pushing it sideways. So let's say it's now maybe over here. A little bit later, the velocity is not going to be in this direction because the force is pushing this particle perpendicular to that. So a little bit later, maybe it's now moving, say, like this way. And a little bit later, the force will still be perpendicular to the velocity. So instead of being in this direction, come on you, don't do that. There we go. Nope, still not behaving. There we go. So instead of being in that direction, it'll be perpendicular to the velocity like that. Now we repeat this argument maybe just one more time because I'm sure you're getting the idea now. The particle a little bit later is not going to be there. Let's say it's here. The velocity vector is not going to be that way anymore because of the force. It'll be bending, like pushing it or giving it a component. So now it might be moving like that, and the force will be perpendicular to the velocity always, so we have a nice constant speed here, but we're changing in direction. And if you look at what's happening here, you should see that this particle is now moving in a circular path. Oh, that wasn't a good circle. Let's undo that one and try that again. After that beautiful build-up, I failed right at the end. Okay, so a nice circular path. There we go. Even that wasn't that great. So if it's going in a circle, then it's accelerating inwards, and there must be an inwards force. Well, that inwards force is the QVB force. So we can write Newton's second law. We can say net force must equal mass times acceleration. But when you're going in a circle, the acceleration is v squared over r. So this is the inwards radial force and the inwards radial acceleration. Now, if we want to find the radius of that circular motion, we cross multiply r up, and we cross multiply qvb down, and we get mv over qb. So for the previous example, we can calculate the radius of the circular motion, putting in the mass and the charge. Again, this will just be magnitude. And when you work that out, you find it's about 2.3 meters. So you would need a really large area there to turn that electron around in a circle, just because it's going so quickly. If it was moving a bit more slowly, with a bit less speed, you'd have less radius. So that concludes our lesson here on magnetic forces. We have a force on a wire, which is LIB, with a right-hand rule. This is L, this is B. I guess you could tell it's L or it's I, direction of the current, direction of the magnetic field. This is the direction of the force on a wire. Then we've got force on a charge is QVB. This would be the direction of velocity. This would be the direction of the magnetic field. This is a force on a positive. A negative would go the other way. And then lastly, we've got the idea that the magnetic force changes the direction, not the speed. It bends particles into a circular path. Oh, thought I was done, but one more topic. A mass spec is an important device in chemistry with some fairly straightforward physics that we can discuss now. There's three regions. Here you get the ions going fast with an electron gun. Here you pass them through a velocity selector, and then they run into a deflection area where they're bent around into a circular path. So each of those regions has some straightforward physics. The accelerating plates, well, that's just the electron gun. Potential energy gets converted to kinetic. The velocity selector sort of combines a couple of ideas that we've discussed before. Here's the idea. Let's say you've got a positive ion, and let's say it's traveling to the right. Now, if the magnetic field is into the page, you can do V cross B. You should find that your thumb is pointing up the page. So that'll be the direction of the QVB force on a positive. Next, think about the electric force. The positive particle is going to be repelled from the positive plate and attracted to the negative plate, both of those pushing downwards. So there's a QE force, charge times electric field, downwards. You can show that for a negative particle, these two will just be turned around and still be opposite. So the electric force would be up and the magnetic force would be down. So with these opposite forces, we can see that, because this one depends on velocity, if the velocity is just right and those two cancel each other out, then the particle will go straight through. Okay? And the condition for going straight through is going to be that those forces balance each other. And then that's only going to happen if the electric and magnetic fields, the ratio of electric and magnetic field is the speed that you're going. So you have to be going at this speed to go straight through. So that's why it's called a velocity selector, because it picks out only particles that are traveling this quickly. Now, if the particles are going too fast, then that means the velocity-dependent force will win. And that for the positive particle, it would be deflected up like this. So the magnetic force would win. If the particle's traveling too slow, then the QVB force will be less, the electric force will win, and the particle will deflect like that. But only for that selected velocity does the particle go straight through, and that's the selected velocity right there. Well, then finally, the particle enters a region where there's only a magnetic field, and we've just seen that in that region there, so the particle comes out like this way, when you have a magnetic field, particles move in a circular path. Okay, that's a much better circle than I did earlier. So with the velocity this way and the magnetic field out of the page, into the page, if you do V cross B, you'll see that the force on a positive ion would be this way, and that force will be towards the center. So the circle is going to be traversed in a counterclockwise sense. And the relevant physics is just the net force, inwards force, which is the magnetic force, equals mv squared over r. Now you can put those three equations together, and then you can solve for something known as the charge to mass ratio, which is relevant for chemistry, but we'll leave that for a homework exercise. So with the mass spec, three regions: accelerating plates, QV is half mv squared; velocity selector, QVB is QE; and then deflection region, QVB is mv squared over r. So that completes our lesson on magnetic forces.